Thanks everybody for coming. It looks like a nice full house, and the stuff we're going to hear about is very exciting. We've been having a conference about it for the last few days. But before we get started, I want to introduce our new incoming director at Las Cumbres Observatory. Our director, Todd Borison, is going to step down at the beginning of August, and so just starting a few days ago to overlap with him is Lisa Story-Lombardi. So maybe she'll tell us a few words.
Hi, yeah, I'm Lisa Story-Lombardi. It's day 3. I've made it through Wednesday over hump day on the first week. They asked me the second day you came back, and I said, well, of course, because Las Cumbres is such an amazing organization, and I'm delighted to be here, delighted to be in Santa Barbara. I've spent the last 20 years at the Caltech and at the Jet Propulsion Lab doing space astrophysics, and I'm quite excited about now being part of this ground-based worldwide network.
All right, so I've known Adam for 20 years or so because we work in the same area studying supernovae and dark energy. We've worked on different teams, but then also the same team. So, you know, I know most of his history, but now he's won so many awards, has so much prestige that I had to write some of them down. He's the Thomas J. Barber Professor in Space Studies at the Krieger School of Arts and Sciences, the Krieger Einstein Professor of Physics and Astronomy, a distinguished astronomer at Space Telescope, a member of the National Academy of Sciences. He's won the Albert Einstein Medal, the MacArthur Genius Fellowship, the Gruber Prize, the Shaw Prize, and in 2011, he was also a co-recipient of the Nobel Prize in Physics. So that went part to Saul Perlmutter, who was the leader of the team that I eventually joined, and then the other part was to Brian and Adam, and it was because of Brian's leadership, but then Adam's hard work writing the first paper discovering the accelerating universe from supernovae, which now we think is due to dark energy. But Adam didn't just stop there and rest on his laurels. He was involved in several other teams after that to try to characterize the dark energy, has been involved in, you know, other next steps that we should do to try to characterize this, but has also gotten involved in local supernovae and trying to measure supernovae very nearby. And that's really hard to do. It requires a lot of resources, learning new areas of science, studying Cepheid variable stars, and so on. And in fact, this conference we've had for the last 3 days is this sort of new era that Adam has helped pioneer. So many people who win the Nobel Prize go on to just become pundits and not do very much. But Adam won it when he was very young, only 41 when he won it, one of the youngest people to win the Nobel Prize. And he's gone on to keep doing great things. And we just had a wonderful 3-day conference. Absolutely not sure if there's new physics involved in this new kinds of discoveries that he's making. But we're very happy to have him here tonight, Adam Riess.
So thank you very much for inviting me here, and I'm going to tell you the story of how observations of exploding stars revealed to us that the universe is not just expanding, that's something we knew before, but actually expanding faster and faster, accelerating, propelled by a mysterious new component of the universe that we call dark energy that we don't know that much about. So before I can tell you about the exciting parts, let me give you a little bit of a primer of how we thought about the universe before this discovery. Okay, so when we look out at the universe, it looks static. This is a deep image taken of the universe. This is not just any deep image. This is the very deepest image ever taken. How do you take a deep image? You take a powerful telescope, in this case the Hubble Space Telescope, and you point at what looks like an empty region of the sky, and you open the shutter and collect light for many weeks. And so you can observe the very faintest things, just like if you've ever done photography, you know, to take an exposure of something faint, you leave the shutter open a long time. So we kept the shutter open many weeks, and what you see are thousands, tens of thousands of galaxies. The faintest that you see are 1 trillion times fainter than anything you could see with your naked eye. And this is really only a tiny patch of the sky. If you took a single grain of sand and held it out at arm's length, you would cover a patch this size. And so that really means the universe is huge and filled with galaxies. And so when you look at an image like this, you get the impression that the universe is static because, look at everything. It's there. If you kept that shutter open for many weeks and things were zipping around, they would look all blurry. We don't see that at all. But that's really a false impression because the universe is actually expanding like it received a big kick that we call the Big Bang, and now the separation between galaxies is growing. You could think of the universe as like a giant loaf of raisin bread rising in the oven. It's like we sit on a raisin and we look at all the other raisins and they're moving away from us. And we assume whichever raisin you're sitting on, the same phenomenon would be seen. So you might wonder, how do we really know this about the universe? And the answer is, we checked. Actually, I checked all the results from this talk just before, so don't worry that I'm making anything up. But really, how would you know this? How could you determine that the universe is expanding? Well, if you remember back to that little animation that I showed, right, the key elements were that things were moving apart, moving away from us. So you want to measure how fast things are moving from us. And you want to be able to measure how far away things are. And those are the two key elements. So I'm going to walk you through how we make those measurements. And the hardest one in this field is to measure how far away things are in space. And so let's review, how do we measure how far away things are? And let's start out with, how do we figure out how far away things are on Earth? We have many methods that we use. Let's see if this is good. One method, the sort of tried and true, is called parallax. If you see a crew of surveyors out on a road and they're trying to measure the distance to that tree and they don't want to swim over that stream there, right? They're going to sight that tree relative to something even further away, like a mountain. Then they're going to move their equipment along some baseline and they're going to sight that tree again, and it will move through some small angle they measure. And they've measured the distance they had to move their equipment and that angle, and they have built a triangle. And if you remember your trigonometry, you can then measure how far away that is without ever going to that tree. That's a nice trick. Alternatively, a method like lighthouses. A ship captain at night wants to be able to gauge how far he or she is from shore. And so they understand that a lighthouse is extremely luminous. And so as long as it looks faint, they know that they are very far from shore. In fact, they can gauge just how far they are from how bright it appears. Now, you could get fooled if you were looking through the light on a foggy day. Then it would look dim and fool you into thinking it was far away, even if you were right up against the shore, right? And so we have other tools we use, like foghorns. A similar principle as the lighthouse, something that puts out a very powerful signal, that its signal weakens by being attenuated over distance. And in the case of the foghorn, that'll cut through the fog. So you want the foghorn to be quiet to tell you you're still very far away, okay? And the fourth method I'm going to show here is what I call objects of known size, okay? So we look out at a distant object, like, you look at this squadron of airplanes here, and you just know that the small ones that you see are small because they should be like the big ones. They're just further away. It's not like, those could have been baby airplanes just flying, with their mothers and fathers all together. But, we recognize that's not the life cycle of airplanes. So these are the ways that we measure distances here on Earth. And what we do in space is a little bit different because we don't have any of these human-made objects, which is, in some ways what all these are. So we have to use what is available in space and telescopes. And one of our best tools that's available in space is more like the lighthouses. When you have a distant galaxy, and this could be one, maybe it has 100 billion stars in it, but at some point in its life, one of those stars may explode and creates what we call a supernova, and that can be as bright as billions of times the luminosity of the sun, and that's kind of like a stellar lighthouse. And let me see if I can get this pointer to make my supernova explode. All right. There we go. All right, so then when a supernova explodes, we know how luminous it ought to be. So this is what astronomers call a standard candle. Any object whose luminosity you understand so well that by measuring how bright it appears, you could tell how far away it is. How do we do that? Well, mathematically, we use the inverse square law, that the brightness will decline as 1 over the distance squared. You could think of that as there's a certain amount of light, and as it goes out further, it has to paint the surface of a larger and larger sphere, and so you get less and less light per little area. And so if it's twice as far away, it'll be 4 times as faint. If it's 3 times as far away, it'll be 9 times as faint. So astronomers like myself and Andy and others look for these exploding stars to gauge distances. But now, how about the other aspect of what I showed you, the fact that the other galaxies were moving away from us? How do we measure that? Well, our supernova or any other kind of standard candle emits light at some known wavelength. These wavelengths are known from the laboratory for the most part. So the wavelengths correspond to colors, meaning that the light is emitted at some color. And then as that light propagates to us, it is stretched by the expansion of space to become a much redder or longer wavelength of light. That's what we call the redshift. Let me see if I can make that happen with this mouse. There we go. So the light propagates to our telescope, and as a result of the expansion of space, it's much redder by the time we get it. And so this is the recession you saw of all the galaxies, or, you know, in the loaf of raisin bread analogy, this is how we see that the raisins are moving away from us, because the light that we receive from them is redshifted by this. Now, this is actually quite an interesting phenomenon, because if you looked at any one galaxy and you saw this redshift, it could be just that it was moving away from us just by chance, moving off in some random direction. But it's the fact that all the galaxies, pretty much, all 99.99% of galaxies have the redshift, tells you that they are all rushing away from us. Now, what's so bad about us? Well, what you come to realize is unless we live in a special place in the universe, if you're sitting on any raisin in the rising loaf of raisin bread, it will always look like this. And so this is really how we know the universe is expanding, because of this pattern, this signature that everybody will see red-shifted galaxies. So now we could get more quantitative than the animation I showed you before. If this will advance to the next slide. There. Oh, hold on. Sorry. I went back. Sorry, this is an interesting system. Okay. And so the same animation I showed you before is on the left, but now we can be quantitative. We can go out and measure the distances and these recession velocities from the red-shifted light, and we can make the kind of diagram that you see on the right. And what you quickly realize is another signature of an expanding universe is the further something is away from us, the faster it moves away from us. Because in this case, there are more grid squares between us and something distant than something nearby. So if you're doubling the size of the grid squares over time, further away things will move faster. It's like the distant raisins in your loaf will move faster because there's more dough between you and them. And so seeing this linear relationship between distance and velocity is the signature of an expanding universe. Measuring the slope of that relationship tells us the rate of expansion of the universe, how fast it's expanding. If that were a steeper slope, the universe is expanding faster. If it were a shallower slope, it would be expanding slower. If it were a negative slope, let me see what pointer will allow me to do this. If it were a negative slope down here, then the universe would be contracting, not expanding. And so we can actually measure the slope and measure the expansion rate of the universe in this way. Now, this is not just a thought experiment. This was first seen by the astronomer Edwin Hubble, who combined measurements of redshifts made at the turn of the past century from Vesto Slipher with his own measurements of distances to nearby galaxies. And so I know this looks a little bit ratty, this graph, but this is the first evidence that the universe is expanding. In fact, this is such an iconic graph. I tell my students, I don't have any tattoos, but if I got a tattoo, I would definitely get a tattoo of this, because that's just how significant it is. Now, in my thesis, I continued making these kinds of measurements using the supernovae, which would go out further. And so just to show you some perspective, the measurements I made in my doctoral thesis, Edwin Hubble's original measurements would fit in the lower left corner. That tiny little red box you see here would fit all of Edwin Hubble's original measurements. So, it's not just nearby. As you go further and further out, the universe is expanding. It's expanding as far out as we can see. Okay, so then click. You might wonder, let's see, I feel like I jumped a slide. Let me try this again. Yes. Okay, so now that you know the universe is expanding and that is something we could quantitatively measure, we can immediately address really interesting questions. Questions that I thought, when I was a kid, you'd ask, a philosopher or a rabbi, like, how old is the universe and when did this begin? But now with these tools, we have a way to tell you, okay? And how does that work? Well, if we measure the universe expanding and we measure it's expanding at some certain rate, now you can imagine running that movie backwards in time at that same rate. It's just using mathematics to imagine running this as a backwards movie. So now instead, imagine everything is contracting at that rate. Just because you're running time backwards in this movie, keep doing it, and eventually everything is on top of everything. That is an estimate of how old the universe is. How long, at the current rate we see the universe expanding, would everything be on top of everything if it were actually contracting instead of expanding at that rate, if we ran the movie backwards in time, okay? Now, that's pretty mathematically close to just taking the inverse of the expansion rate of the universe. Now, when Edwin Hubble first measured the expansion rate of the universe, he got a very large number, which the inverse is a very small number. That implied the universe was very young. He got an answer that the universe was only 1 billion years old. Now, we knew that the Earth was older than that in the 1920s, so something was wrong with the initial measurements. However, we didn't quit there, and in fact, I just came back from a conference where, this marks about 100 years, 120 years we've been trying to improve the measurement of the expansion rate of the universe. And we've made a lot of progress. This is from an article in the New York Times giving you the long history of trying to measure the expansion rate of the universe. And there were some very important developments along the way. I'm going to try to use the hand microphone, I think, to maybe I can pull that off here. So certain developments along the way, like the discovery that there have been multiple generations of stars had an effect in the previous measurements, as well. Oops, I wasn't going there yet. As well as the use of better digital detectors, the launch of the Hubble Space Telescope, the ability to measure distances from supernovae. All of these contributed to great improvements in our ability to make these measurements, so that if you just look at the last 30 or 40 years, things really started to converge. And what I was presenting at this conference just a couple days ago was what I think is the best measurement to date of the expansion rate of the universe, which implies that the universe is around 13 to 14 billion years old. So comfortably older than the Earth and oldest stars in it. Now, you might wonder, okay, all right, I believe you. The universe is expanding, and we can tell how old it is. But your real question might be, what happens after that? I mean, is this going to go on forever? What is the fate of an expanding universe? And this reminds me of the question that Isaac Newton wondered, which is, what is the fate of a cannonball when you fire it from the surface of the Earth? Okay, he imagined firing that cannonball with greater and greater velocity. Of course, it'll get further and further. And then the question is, will the cannonball fall back to Earth, or will it escape the gravitational pull of the Earth? Will it go into orbit, or will it escape altogether? And so what matters is how fast you fire the cannonball given the Earth. Or if the cannonball was fired at some certain velocity, what would matter is what is the mass of the Earth, and can it hold back that cannonball? So there's a very special velocity that people who build rockets know as the escape velocity. If you fire it faster than that, that's for the mass of the Earth, it will escape. Less than that, and it won't. So this was the question we had about our universe. Will it expand forever? Does it have escape velocity from itself, from the self-gravity of the universe? Or is there so much matter in the universe that the attractive gravity will stop the expansion and have it fall down, like firing that cannonball on a very heavy Earth? It wouldn't escape. So now this is a slightly different thought that Einstein had. Einstein, in 1916, was developing his new theory of gravity called general relativity. And Einstein had been given some bad information by astronomers of the day. He had been told that the universe was static. So this whole idea of the cannonball moving out, or the universe moving out, that wasn't even something he was thinking of. And he was confused about why the universe would even be static, because he realized even if the universe was static for a moment, all the galaxies were out there, and whoever was holding them in place let go, gravity would then start to bring them together. It's sort of like saying if you took that cannonball and you just held it out into space and let go, it will fall, okay? And so if somebody told you that cannonball was just hanging there, it wasn't falling, right, you'd say there must be something opposing gravity to keep it static. And he made an amazing discovery. He discovered that in his theory of gravity, called general relativity, that while the gravity of objects in space is attractive, just like in Newton's gravity, in Einstein's theory of gravity, the gravity of empty space itself could be repulsive. He called this property the cosmological constant, and we would call this dark energy today. The fact that space can have repulsive gravity while stuff has attractive gravity. And so he thought these two were in kind of a perfect balance. Now, what changed was then 10 years went by, and he learned from Edwin Hubble and others that the universe was expanding, and that this whole idea that he needed to keep the universe static was completely out the window. He famously, in 1931, he goes to visit Edwin Hubble because he wants to see for himself if this is really true, and he visits out to the telescope. You see that picture over there, Einstein looking through the telescope, Edwin Hubble is looking on. I figure this must be just a publicity shot because, even then, Hubble was looking at very distant objects that you couldn't see with your naked eye. You had to use a photographic plate and add up light for a very long time. So when Einstein is looking through, he's not seeing anything. He can't see anything that Hubble is able to image. But, he's a theorist, so maybe he doesn't know that and is too shy to ask. I don't know. It would be probably unusual for Hubble to be smoking his pipe too. That's why I think this is a PR shot. But anyway, I like the picture of the two of them together. Okay, so all right. So you might wonder. All right. So let's get rid of this idea of the universe being static. And Einstein invents this dark energy thing, but we don't even need it, right? Hubble's already showed that the universe is expanding. Now let's go back to the cannonball. We want to know what's going to happen. Is that cannonball going to fall back to the Earth, or was it fired with escape velocity? Will the universe escape its own gravity? And the normal way you figure these things out is you just keep watching and waiting. You watch that cannonball and you map its trajectory. But things change very slowly in the universe. We can't just sort of wait quarter by quarter like the economy and see if it's going up or down, okay? So instead, we have to use a trick that astronomers had known about for a long time. Did this jump? Yes. Which is actually the information we get from distant objects in the universe is never telling us about the present state of the universe anyway. It is always telling us about the past state of the universe. That is, the universe doesn't instant message. It doesn't give us information instantaneously. There's a delay. And that delay might be, for example, if you're looking at a distant standard candle that's very far away, that delay is the distance over the speed of light. And so you might be really learning about how fast the universe was expanding 1 billion years ago. It's like any distant object you look at in the universe, it's telling you about the past. If you found a more distant standard candle, it might tell you about how fast the universe was expanding 2 billion years ago. And a further one 3 billion years ago. Well, what seems annoying that we just can only get delayed information is actually a powerful tool. It is a way that we can look at the expansion history of the universe. We could see everything that has happened in the past just by looking further and further out. And so we can look at the past trajectory of the universe. Like that cannonball, we can see whether it's on a trajectory to land back on Earth or whether it's on a trajectory to escape. Now, in the 1990s, my colleagues and I were looking at this, and the people in the field thought that there were two sort of likely possibilities. One is, as I said, the universe was chock-filled with matter. The attractive gravity was greatly slowing the expansion. You would see that if you looked in the past trajectory that the expansion was slowing down a lot. And that kind of a universe we defined by a quantity called omega. And if omega was greater than 1, then it was this very heavyweight universe. And it would stop expanding, start contracting, and it would end in a kind of big crunch, the opposite of the Big Bang. Not that movie Run Backwards, but that movie continuing on and reversing and eventually contracting. Alternatively, we could have lived in a very lightweight universe, very little matter. And so there's not a lot of gravitational braking going on, and the universe would just expand forever. Or we could have lived on the knife edge case. It's sort of like what it takes to put that cannonball into orbit. It's just enough, sorry, let me rephrase that. What it takes to just get that cannonball away from the Earth, what we call truly escape velocity. That the universe would be expanding forever, but slowing in its expansion, sort of reaching infinity and running out of speed. And so we wanted to make measurements like this, and we realized the way to do this was to use measurements of supernovae very far away, these standard candles. Now, not every kind of supernova will work for this. There's a very special class of supernovae called type 1As, which make the best standard candles. The famous Indian astrophysicist Chandrasekhar explained more or less in the 1930s that a certain kind of star, a white dwarf star, the core of a star at the end of its life, our sun will become a white dwarf at some point, that kind of star can only be stable, can only exist up to a mass known as the Chandrasekhar limit. And if that star gets a little more massive than that, then it will get a runaway thermonuclear explosion. It's like nature's own standard nuclear bomb. And so astronomers came to realize that many of the supernovae we saw were Chandrasekhar's white dwarfs living next to another star, collecting a little matter, crossing that threshold, and going boom. And that provides an outstanding standard candle because they're always exploding at more or less that same threshold. And so we realized if we could go out and look for these far away, we could compare how fast the universe was expanding back then, far away back then, to the present. I'm just going to make the jump. Okay, so you might wonder, how is it that we actually find these supernovae? These are 4 that I studied in my thesis. You see the big galaxy. And the answer to how you find the supernovae is actually pretty simple. They're the dots at the end of the arrows in those pictures. And no, but you might wonder, how do we, this is with Photoshop, I put those in. How do you actually find them? I mean, we look in the sky, I've never seen the arrows. So we actually have to find them. And how do we do that? Well, finding a supernova is a little bit like winning the lottery. And so if you buy one lottery ticket, you're not going to win. And you're not going to find a supernova if you stare at one galaxy and wait for something to go supernova, because there's a supernova in a galaxy like ours only once every 100 years. However, if you instead look at 100 galaxies over a year, then there'll probably be one supernova. And this is sort of now more like buying 100 lottery tickets. Maybe you got a shot now, right? Instead, buy 1,000 lottery tickets and you'll find 10. And so what we as astronomers do more or less is we buy all the lottery tickets, and we guarantee that what seems like an intrinsically unlikely event actually occurs all the time. And then we enlist computers, which are very good at taking these very large images of the sky, separated maybe by a month or a week or something, and digitally subtracting them and finding the lucky lottery ticket, the new point of light, and that indicates the presence of a supernova. So in the 1990s, my colleagues and I started a project to measure how much the expansion of the universe was slowing down, how much it was decelerating, thinking that that would answer this question. Is it decelerating enough that it's eventually going to stop expanding, start contracting, and end in a big crunch? Or is it decelerating only a little because it has escape velocity from itself and it would just expand forever? That seemed like a pretty interesting subject to research. So come about 1997, I was a postdoc at UC Berkeley, and I was very fortunate to be picked to lead the analysis of our team's first large set of data. And I was analyzing the data, and there's a very simple relationship shown up in the upper right that the amount of deceleration of the expansion weighs the universe. It tells you how much mass there is. If the universe is decelerating a lot, that's because there's a lot of mass. If it's decelerating a little, there isn't much mass, and that's what tells you which of those cases you're in. Now, when I analyzed the data, I wrote a simple computer program to tell me, okay, which is it? What is the mass of the universe? Is it the little or the lot number? And so this is a key page from my lab notebook where I finished the analysis, wrote the computer program, and wrote down the number the computer program got. And so I was looking for the number to either be small, like 0.3, or more than 1, the magic number that would tell us that it was going to crunch. And instead I saw a negative number, and that didn't make any sense because mass can't be negative, so how can that be? Well, the problem was that I hadn't really looked enough at the data to notice that the universe was not decelerating at all. It was actually accelerating. And computers don't really know physics, and so if you give them an impossibility to, say, equate deceleration with mass, and then you change the sign of deceleration, that it's actually accelerating, the computer goes, okay, I can do that. I'll just change the sign of mass, right? But that isn't the right physics. The right physics is to recognize what Einstein had first recognized, that there's another possibility, that the gravity of empty space could be repulsive, that you can generate acceleration with Einstein's term, that term there, which has the negative sign in front of it, can do the other thing. And so this was the first indication that I had that about 70% of the universe is represented by that term. Now, of course, I didn't think this right away. I thought, oh, this must be a mistake. But I spent a lot of time doing more calculations, first of all, to make sure that this was even what scientists call significant. And after doing some of those calculations, I determined it was significant enough, especially if there's any matter in the universe, to go ahead and begin discussing this. And then I began discussing it with my colleagues. So I worked on a team of 18 people, and it's really interesting to look at the email dialogue that went in over the course of 24 hours as I first began talking to the rest of my mostly senior colleagues about what we were seeing in our data and what this really meant. So here are those emails. If I don't fall off the stage here. Alex Filipenko, who was a professor in Berkeley I was working with at the time, broke the news to our team on January 10th, 1998, saying, Adam showed me fantastic plots before he left for his wedding. Our data imply a non-zero cosmological constant. Who knows? This might be the right answer. So he was leaning forward. But Bruno Leibengut in Germany, also on our team, concerning a cosmological constant, I'd like to ask Adam or anybody else in the group if they feel prepared enough to defend the answer. There is no point in writing an article if we are not very sure we are getting the right answer. And this is a lesson into scientists. We tend to be very conservative because most new things you see are wrong. And so, that usually seems like the smart bet. And nobody wants to look like a jerk or stupid by, making a wild claim. Brian Schmidt, my colleague on the team who really led the efforts to find the supernovae, was in Australia, and he wrote, I agree our data imply a cosmological constant, but how confident are we in this result? I find it very perplexing. My thesis advisor, Bob Kirshner, writing from Santa Barbara, which he was on sabbatical on at the time, wrote, I am worried. In your heart, you know the cosmological constant is wrong, though your head tells you that you don't care, and you're just reporting the observations. It would be silly to say we must have a non-zero cosmological constant only to retract it next year. Mark Phillips at Chile responded, as serious and responsible scientists, we all know that it is far too early to be reaching firm conclusions about the value of the cosmological constant. John Tonry, my colleague in Hawaii, who remembers the detection of the magnetic monopole and other gaffes. On the other hand, we should not be shy about getting our results out. Alex Filipenko responded, well, if we're wrong in the end, then so be it. At least we ran in the race. What he meant by the race was the fact that there was another team located at Lawrence Berkeley National Lab, which actually Andy came to work with later, that was doing the same experiment at the same time. And so we knew that. And so there was kind of a race between us to see who was going to be the first, we thought, to measure how much the expansion was slowing and what the fate of the universe was. So this was quite a surprise, but we didn't want to come in second place in that either. I wrote, after I came back from my wedding, packing quickly for my honeymoon, the results are very surprising, shocking even. I've avoided telling anyone about them because I wanted to do some cross-checks. I have, and I wanted to get further into writing the results up. The data require a non-zero cosmological constant. Approach these results not with your heart or head, but with your eyes. We are observers, after all. Alejandro Clocciati, an astronomer in Chile on our team, wrote, if Einstein made a mistake with the cosmological constant, why couldn't we? I never knew if that was supposed to be reassuring or not, but I guess if you make the mistakes of people who are smarter than you, there's no shame there. Nick Sunsef in Chile, I really encourage you, Adam, to work your butt off on this. We need to be careful. If you're really sure that the cosmological constant is not zero, my God, get it out. I mean this seriously. You probably never will have another scientific result that is more exciting come your way in your lifetime. And Nick was usually right. And so we went ahead with this paper saying observational evidence from supernovae for an accelerating universe and a cosmological constant. The other team followed very shortly after. And so both teams were basically saying that the universe was about 70% in this form of dark energy, or cosmological constant, as Einstein would have called it. And this was the breakthrough of the year for Science magazine in 1998, that even Einstein himself would have been amazed. You know, he made this sort of discovery, theoretically, then he threw it away when it wasn't necessary, and then it had come back out as necessary. And so, in a funny sort of way, it was a great triumph for Einstein, I would say. But to be more specific, you know, why is the universe actually accelerating? And what's so fun about this, or interesting, is we don't really know. We don't really understand this physics well. We have three sort of ideas we're running through, sort of in order of most likely. One is literally what Einstein had suggested, the cosmological constant. But to a modern-day particle physicist, they would call this vacuum energy, or the energy of empty space. That empty space is not empty, but it is a sea of virtual particles appearing and disappearing, and there's an energy associated with that. And this is actually not an option. This is a requirement of quantum mechanics. But the amount that we expect is very different than the amount we see. So this is a big mystery to us. Another possibility is that we have a temporary form of option one, that we have what's called dynamical dark energy, that it's just the energy of a field. Think of any field, you know, the magnetic field, the electric field. This would be some field. It has energy, and so it temporarily acts like option one, but it might go away. And option three is that we have broken gravity, that looking on the largest scales of the universe, we are seeing some behavior which doesn't follow Einstein's theory of gravity. Now, I think that's pretty extreme, especially given that the phenomenon we're seeing fit quite well into Einstein's theory. He was the first person to come up with it, but you always have to keep that in mind. However, in 1998, 1999, at this time, we worried, what if we're just wrong for a much more uninteresting reason? What if what we're looking at are distant supernovae? And you remember the example I gave you of the lighthouse. If on a foggy day, if you look at a lighthouse, it fools you into thinking that you're much further away from it than you really are. Well, what if there was kind of a fog in the universe? What if there's kind of a dust out there that is misgauging our distances? Or what if the supernovae born that long ago were just born fainter? And so we worried about that. So here's the scenario here. Either a faint supernova means it's far away and there's dark energy, or a faint supernova looks faint because it's not far away at all. It's just looking through a lot of dust. And so we worried about this. However, we also recognized that this dimming effect from dust, if that's what was going on, would continue as we looked further and further out into space, more dust. Whereas if this effect was really due to dark energy pushing things apart faster, when the universe was younger and everything was more compact, the universe would have felt the attractive pull of matter, dark matter, much more, and so you would not see this continued dimming, that the separations would stop becoming so large. And so we saw a way to test these possibilities, but it required us to be able to find much more distant supernovae than we ever had before. So we had to turn to a more powerful telescope to find these extra distant supernovae. So let me give you a brief primer here on the history of building more and more powerful telescopes. Here is the sort of last 400 years improvements in sensitivity over the eye. And it's gone up quite dramatically. Galileo got us almost a factor of 100. Then larger telescopes and better locations got us more and more sensitivity. Stop using our eyes and using photographic plates or electronic detectors helped. Then when the Hubble Space Telescope was built, it was put above this great ocean of air above us that blurs the images that we see. So, for example, what you see there on the side is 2 images of a distant supernova and its host galaxy. One from the ground, you can see how difficult it is to separate those. One with the exquisite resolution from Hubble because it's above the atmosphere. And then sometimes you're lucky and the astronauts go back to Hubble and put new generations of detectors on there. And so that's how we see things that are 1 trillion times fainter than your eye, with sensitivity improved by a factor of 1 trillion. And so in the early 2000s, I led a project with Hubble to find the most distant Type 1a supernovae using new cameras they had recently installed. And from that work, we were able to rule out all those other ideas about fog in the universe, supernovae being born fainter. It really seemed like the supernovae were really telling us this story, that the universe is accelerating now. It was decelerating in the beginning when matter was much closer together and had more of an effect. But as the universe dilutes by expanding, spaces are getting greater and greater. And now this dark energy does appear to be taking over and pushing things faster apart. Of course, in science, we never believe anything from usually one line of evidence. We still worry if something is wrong. And so, just like earlier in this talk, I showed you 4 or 5 different ways to measure distances. We astronomers have 4 or 5 different ways to gauge the expansion of the universe and this effect. So, supernovae in 1998 were just the first to show the universe was accelerating. There was another effect seen in the early 2000s where photons from pieces of light from very distant objects would cross deep gravitational wells from clusters of galaxies. They actually gain energy when they fall into those potentials. They lose energy when they climb back out. Those are supposed to balance, but dark energy was prying apart those potentials and allowed astronomers to measure how much dark energy. And the answer they got was the exact same amount we saw from the accelerating universe. This is called the integrated Sachs-Wolf effect, kind of technical. Another method that was used was to measure the geometry of space itself, which tells you what the total sum of all energy and matter in space is. Then astronomers measured just the amount of matter, and when they got an amount of everything that's in our units 1, and the amount of matter in our same unit 0.3, the 0.7, the 70% showed up as the same amount we saw the other 2 ways. Then another effect, people can see the largest clusters of galaxies, which pull in new galaxies by gravity, have become less and less able to do that because of dark energy. And also we've seen a change in the absolute scale of the universe from shortly after the Big Bang to now that can't be explained without the same amount of dark energy. So we have many independent lines of evidence for dark energy, but the way we really knew that this was true was because we won the Nobel Prize. And the Swedes don't give you the Nobel Prize if you get it wrong, I think. So anyway, this is when I knew that this was really legitimate. And so we went to Stockholm in December of 2011. We had a great time. Our whole team came out. We had all kinds of great activities and a lot of celebration. But all this celebration kind of hides a dark side to this discovery, which was well described I think that same month or 2 on the show Big Bang Theory, where the characters were talking about, well, they were watching us in Stockholm receive this award and talking about what the meaning of this actually was. Let me see if I could play this. I move the mouse and an arrow should arise, right? Click. Okay.
It's 2 a.m. What are you doing up?
Nobel Prize acceptance ceremony streaming live from Stockholm.
Sure. I want to see what all the scientists are wearing this year.
Look at these men. They've managed to win the top science prize in the world with no more understanding of the quantum underpinnings of the expansion of the early universe than God gave a goose. You should...
Right, so we're guilty as charged there. That's exactly a perfect explanation. We have just observed that it's accelerating, but without understanding what he said, the quantum underpinnings of gravity, we can't really explain this. So he was kind of, making fun of us, and rightfully so. So what we've come to understand about the universe is pretty breathtaking. I mean, if you're an optimist, you still have to be impressed that for the first time we've been able to describe the whole universe and give words to everything, and have a basic understanding of their role in the universe. And so about 0.05% is in planets, about 0.5% in stars, 4% in gas. You add all that up and you're at less than 5%, and that's what's made out of atoms, the atoms we're familiar with, the stuff we know of, like us. Then there's 25% in an exotic form that we call dark matter. We think it's a cold particle without interactions, but we have yet to identify it in the laboratory, although it seems absolutely critical to hold galaxies together. They would not stay together. The stars would wander off. They're moving way too fast. And galaxies themselves wouldn't stay in clusters of galaxies. They are moving way too fast. So there's much extra gravitational glue in the form of dark matter. And then there's the dark energy, even more mysterious, but only seen really effectively between the galaxies into deep space. It seems to be accelerating the expansion. So we're not resting on our laurels. The astronauts went back in 2009. They serviced Hubble for the last time when the space shuttle was still working. They put the Wide Field Camera 3 in, and that's what I've been using for my work in recent years. We've used it to find even more distant supernovae, and we have used it to improve our measurement of exactly how fast the universe is expanding. It was known to about 10%, and now it's known to just better than 2%. However, in doing this, we have discovered a new problem. Even though we thought we finally at least had described what the universe is made of, we now have the ability to perform a kind of end-to-end test of the whole story. We go all the way back to the beginning, and we look at the radiation left over from the Big Bang, what's called the cosmic microwave background, and analyzing that radiation allows us to predict how fast the universe should be expanding today. And that prediction is very precise. It's good to about 1%. However, when we actually measure how fast the universe is expanding today, we get a number that's about 9% faster than the prediction. Okay, this would be like, having a child and having their height measured and using a growth chart to tell you how tall they're going to be when they grow up. Maybe they predict, the doctor says they'll be 6 foot tall, and they come out 7 feet tall. What happened? And so that's what we've been wondering. It looks more or less like you see here, that we basically have two stories for the universe, two parallel stories that are very similar, but they start at different times, and they lead to different expansion rates of the universe. So not only are we not quite able to go from end to end and explain everything, we're also a little confused these days about exactly how old the universe is, because if the story from the beginning, the Big Bang story and projection is right, then the universe is probably more like 14 billion years old. But if the expansion we measure around us today is right, then it's probably more like 13 billion years old. What's much more important is that the prediction doesn't match the observation, and this suggests to us that we are still missing something in our understanding. It may be an extra wrinkle about dark energy or dark matter. It may be another dark component in the universe. And so this conference I was at for the last couple days here, astronomers were wrestling with exactly this issue. What are we missing? Why don't these two things agree? What's going on? Again, if you're an optimist, it's pretty impressive. We go over a 14 billion year span in the history of the universe, making a prediction shortly after it begins and checking at the end, and we're only off by 9%. But we're stubborn scientists. That's not enough. When the error bars get down small, that is too much, and that tells us there's still something that doesn't quite fit. To try to understand this, new satellites are being developed. The Europeans are building one called Euclid, and that will launch in a few years. NASA is building one called WFIRST. These are telescopes like the Hubble, but they're dedicated largely to studying dark energy and helping resolve some of these puzzles. And we're really looking forward to the use of those. So I want to end this talk with just sort of justifying, why do we study dark energy? Why is this so important? Well, it is most of the universe. It's really hard to say we understand the universe when the biggest piece is a total mystery to us. It will help us determine, and our understanding would help us determine the origin and fate of the universe, because dark energy is so dominant. It controls the fate of the universe. It is controlling the dynamics, and until we understand that, we can't really say what the ultimate fate of the universe is or how it started. But the most important reason for studying dark energy is understanding dark energy lies at the crossroads of really our two most successful theories in physics. We have one, it's almost like a rule book for how the universe operates on atomic scales. That's called quantum mechanics. And then we have another rule book, another theory called general relativity, Einstein's, which is the macroscopic, how the universe operates on large scales. And these two theories are incompatible. We've known that for a long time. And very smart physicists are always trying to figure out how to unify those. Well, the universe knows how to do that, and in the phenomenon of dark energy, it is sort of showing us how to do that, because it goes from the atomic scale, where it describes what is empty space and what is in the vacuum of space, and how do you add that up then and apply it to the whole universe. There's something we don't understand there, and so it's always nice to have a clue when you're stuck. And so we think by studying the dark energy, we may have a better chance of learning how nature does physics at that interface. So I will end there, and thank you for your time.
Thanks, Adam. We're going to open the floor for just a couple questions, if that's okay. Sure. And we will then have some snacks outside. So if anybody has a question, please raise your hand. I'm going to bring you the mic.
Thank you for your presentation. So a question I have is there expansion within galaxies as well as between galaxies?
No, that's a great question. When matter is dense and close together, and that happens in galaxies and it happens in our solar system, then it dominates, because just like in Newtonian gravity, it's also true in general relativity, that gravity depends on the separation squared between two objects. And so when objects are very dense, when objects are close together, they feel that gravity and they ignore the dark energy. It's only when they're so far apart that the attractive gravity has been so greatly diluted by objects being far apart that this very light background repulsion is noticed and really kicks in. So you don't see it in galaxies, you don't see it in the solar system, you really only see it in deep space, even though the dark energy is around us here in this room. In fact, we could show it to you on the screen. That's what we're very good at. Can we get that slide back? Okay, sorry. All right.
Do you have data that indicate when the acceleration of the expansion began, and whether the universe was slowing down prior to that?
Yeah, so the best data shows that it would have been about 5 billion years ago. So out of a universe 13 or 14 billion years old. So it's recent. In fact, it's around the time that the Earth and the Sun first formed. But it's not a moment when something suddenly happened. You'd be, it's like watching, if your car was in neutral and it was rolling downhill and then suddenly it was coasting. It would just be a gradual change like that.
Hi. So you can track when the Big Bang happened. Could you track it to where, like a region of space where the Big Bang actually happened?
So the mysterious thing, the hard thing to get your head around is that there's no where. It's everywhere. It's all around us, like the loaf of raisin bread. I should have mentioned that loaf of raisin bread might be infinite. And so, you come to realize that in an infinite loaf of raisin bread, whatever raisin you're on, you look at the other ones and they are certainly moving away from you. So you write in your lab notebook, everything is moving away, right? And, if you are lucky enough, you could hop on another raisin. You go, everything's moving away from here too. And you go, and it was just like the other raisin when I was sitting there. And you come to realize there is no unique center. This phenomenon of expanding is around all of us. Now, Is it infinite? Does it go out forever? I mean, we don't really know for sure. We can only see out so far to begin with. We can only see out to the horizon, which we astronomers define as the speed of light times the age of the universe. As far out as that, things keep going. But a lot of our theories suggest that it probably is infinite.
At some point where acceleration just spreads the universe so far apart, why do we assume that the laws of physics, whether they're,
Right.
standard or
Will they change?
Yeah. Why do we assume they work? Or do we not assume
So
they work?
far, we see that the laws of physics, the laws of gravity, things like that, do not seem to depend on how dense things are. And so what you're talking about is, in the future, things will be really vacuous. And we see vacuous regions in space, and we can check gravity, and it seems to operate normally. So we have no reason to think that, in fact, the laws of physics as we understand them don't have an expectation that they will change. Now, that doesn't mean that there couldn't be something else going on, and that, if somebody did a great experiment and found something changed that wasn't supposed to, we'd have to revise our understanding of physics, but we don't expect that. At really, really high energies? Well, yeah. Yeah, but we're actually talking about the reverse, the very low scale, but yeah.
I'm trying to understand the idea of being in different points and still seeing the expansion happening.
Mm-hmm.
So I can understand at the center of the universe, there must be a center.
No center.
Okay.
Uh-oh.
Several centers.
I lost half the audience on that one.
Well, okay, so
okay. I know
hypothetically.
it's hard, but let's do this. Infinite loaf of raisin bread.
Yeah.
Okay? Raisins, you're on one. It's getting bigger. You don't know what's going on as far. You can only see out so far, but all you know is you keep checking all the other raisins, and they're further and further apart, right? And you call your cousin who's on another raisin, and you go, "What's the view over there?" And he says, "Everything's getting further and further apart." You call your whole extended family; they're spread out over all the raisins, and everybody is seeing the same thing. That is what it will look like. That is what it's like to be in a universe where there is no unique place and there's no unique center.
Well, my question is then, from 2 points, if they're both expanding outward from both points, all the way around, 360 all the way around, three-dimensionally, how is it possible that it's expanding outward from one point, outward from another point, and you're still seeing an expansion? It looks like they're going to be pointing towards each other, expansion.
It's like, I could do this in one dimension, but if I had a rubber band here, I'd be pulling it apart, and my raisins would just be marks on the rubber band. And as I pull it apart, you could be sitting on any mark, and all the other marks are moving away from you. It doesn't matter which one you're on. And so that is the reason. They're not moving towards each other. All spaces are getting bigger. There is more space all the time, and so things are getting further and further apart. They're not moving towards each other. Everything is separating.
Okay, last question, and then Adam will stick around, as will people from LCO. You can come talk to us while we get snacks. But very last question.
So if you want to summarize your research graphically, what they thought initially was this was distance and the velocity was linear
Right.
with a constant slope,
Right.
but now it's not linear. The slope is
It
increasing.
bends, yeah.
So so you realize that by going further out.
By going further out, we realized,
Okay.
you know what, actually, we're looking further back in time, and so there's no reason that line would always have that same slope.
Okay.
If you look at further back in time, that line will bend.
So it could be parabolic or exponential.
Correct.
Or
And so by measuring that, we found, the bend is changing. It is speeding up.
changing at? What would be a curve fit for that?
I could just tell you the expansion rate today in units that might mean something. The universe will double again in about 10 billion years. That's probably the most graphic rate I could give you.
Thank you very much.
Sure.